Imagine a city that was not designed for people to live in. No apartment blocks, no shopping districts, no office towers. Instead, this city exists for a single purpose: to test trains. In a remote region of China, engineers have built an expansive experimental zone where tracks stretch across open land, control centers monitor non-stop data streams, and sleek vehicles glide above rails without ever touching them. No wheels, no steel-on-steel contact, just magnetic force. China has quietly constructed what can be described as a hidden Maglev test city, a full-scale research environment dedicated to perfecting ultra-high-speed magnetic levitation trains that could one day travel as fast as aircraft. It is not a tourist attraction. It is not a public transit line. It is a laboratory at the scale of a city. And it raises a powerful question. Why is China investing so heavily in technology that most countries still consider experimental? Maglev is short for magnetic levitation. Instead of using wheels that roll along tracks, Maglev trains float above a guideway using powerful electromagnets. Magnetic forces lift the train a small distance off the track and keep it centered, eliminating physical contact between vehicle and rail. This single change transforms how trains behave. Traditional trains lose energy to friction at every point of contact: wheels, bearings, rails, and mechanical components. Maglev trains remove most of that friction. The only major resistance left is air. Because of this, Maglev vehicles can reach speeds far beyond conventional high-speed rail. While most high-speed trains operate between 250 and 350 kilometers per hour, operational Maglev systems have exceeded 430 kilometers per hour in regular service. Experimental systems have gone even faster. China already operates the world's fastest commercial Maglev line in Shanghai, connecting the city to its international airport at speeds over 430 kilometers per hour. Japan's superconducting Maglev test trains have reached speeds above 600 kilometers per hour. At these velocities, trains begin to compete directly with short-haul flights. But speed is only part of the appeal. Maglev trains produce less mechanical wear because there is no wheel-to-rail contact. This can reduce long-term maintenance costs. They also generate less noise from rolling friction and can deliver smoother rides. From an energy perspective, Maglev systems can be highly efficient at high speeds, especially when powered by electricity generated from low-carbon sources. For countries planning future transportation networks, Maglev represents something bigger than a faster train. It represents a different class of ground transport, a potential bridge between conventional rail and aviation. And China wants to master it. Unlike public rail projects that are announced years in advance and marketed to citizens, China's major Maglev research facilities have largely developed outside the spotlight. Several large-scale test zones have been established in different parts of the country, often attached to universities, state-owned engineering firms, or national research institutes. One of the most prominent is located near Qingdao in Shandong province, where China's first commercial Maglev line was developed, while other experimental centers exist in central and southern China. These sites function as closed research environments rather than passenger transport systems. They contain long test tracks, laboratories, manufacturing halls, and control centers, all dedicated to refining Maglev technology at full scale. Access is restricted and public information is limited compared to conventional infrastructure projects. This controlled setting allows engineers to conduct repeated high-speed trials, failure testing, and system upgrades without the operational constraints of carrying passengers. Over time, these research zones have grown into self-contained complexes with their own power supply systems, data centers, workshops, and support buildings. When viewed from above, they resemble small industrial cities, even though their sole purpose is experimentation. This is why some observers describe them as hidden Maglev test cities. Not because they are secret in a military sense, but because they are not designed for public use or visibility. China's strategy is clear: master the technology in isolation first, then deploy it widely later. Inside these test cities, engineers are not working on a single Maglev design. They are testing multiple generations of vehicles and track systems simultaneously. Some trains use electromagnetic suspension, where electromagnets actively pull the vehicle upward toward the guideway. Others explore superconducting magnetic systems that use extremely strong magnetic fields to achieve stable levitation at higher speeds. Long stretches of dedicated test track allow vehicles to accelerate, cruise, brake, and repeat these cycles thousands of times. Sections of track are built with different materials, shapes, and structural supports to study wear, alignment stability, and thermal expansion. At speeds approaching 600 kilometers per hour, even millimeter-scale imperfections can become serious safety risks. The vehicles themselves are packed with sensors that measure vibration, temperature, magnetic field strength, structural stress, and aerodynamic behavior. High-speed cameras track airflow around the train body, while onboard computers continuously adjust levitation height in lateral position. Automation plays a major role. Most experimental maglev trains are designed to operate without drivers, relying instead on centralized control systems and redundant onboard computers. Engineers use these test environments to simulate emergency scenarios, power failures, sudden braking, and component malfunctions. What is being built inside these facilities is not just a faster train, it is an entirely new transportation platform. Building trains that float at extreme speeds introduces engineering problems that do not exist in conventional rail systems. One of the biggest challenges is stability. At hundreds of kilometers per hour, even small disturbances can amplify into dangerous oscillations. To solve this, maglev systems rely on active feedback control. Sensors measure the train's position thousands of times per second, while computers instantly adjust magnetic forces to keep the vehicle centered and level. Power delivery is another major challenge. Maglev trains draw electricity continuously to maintain levitation and propulsion. Engineers must design substations and power rails capable of delivering enormous electrical loads with high reliability. Backup power systems are integrated throughout the network to ensure that levitation can be maintained long enough for trains to stop safely if the main supply fails. Heat management also becomes critical. High-speed motion, electromagnetic equipment, and power electronics generate large amounts of heat. Cooling systems using liquid circuits, heat exchangers, and forced air ventilation are embedded inside vehicles and guideways to prevent overheating. Precision construction is essential. Maglev guideways must be built with tolerances far tighter than conventional rail tracks. Over long distances, the alignment must remain within millimeters. To achieve this, China uses prefabricated guideway segments manufactured under controlled factory conditions and installed using laser-guided positioning systems. Each of these solutions is being refined inside the test cities before being applied to any commercial deployment. China's experimental maglev systems are targeting operating speeds between 500 and 600 kilometers per hour. At these velocities, a trip between cities 1,000 kilometers apart could take roughly 2 hours, placing maglevs squarely between conventional high-speed rail and short-haul aviation. This speed range is not theoretical. Chinese engineers have already unveiled prototype maglev trains designed for 600 kilometers per hour, and test runs on dedicated tracks have demonstrated performance approaching these levels. However, maglev is not intended to replace all transportation. Its strength lies in medium to long distance corridors where travel demand is high and flight congestion is severe. Routes between megacities such as Beijing to Shanghai, Guangzhou to Shenzhen, or Wuhan to Chengdu are often cited as potential candidates. In these corridors, maglev could offer downtown-to-downtown travel times competitive with airplanes, without the delays associated with airports and security screening. For China, this represents a strategic advantage. Faster ground transport strengthens economic integration between regions and reshapes how distance is perceived. China's interest in maglev is not driven by curiosity alone. It is driven by national strategy. China already operates the world's largest high-speed rail network, with more than 40,000 kilometers of track connecting most major cities. This network has reshaped domestic travel, reduced reliance on short-haul flights, and strengthened regional economic integration. Maglev represents the next step. If high-speed rail connected China's cities, maglev could compress them. Ultra-fast ground transport shortens travel times between economic centers, allowing companies to operate across wider regions as if they were single metropolitan areas. Labor markets expand, supply chains accelerate, business travel becomes same-day round trips. There is also a technological competition element. Japan and Germany pioneered early Maglev systems. China does not want to remain a customer of foreign technology. It wants to become the dominant developer, manufacturer, and exporter of next-generation rail systems. If China perfects reliable, high-speed Maglev first, it gains the ability to sell entire systems, trains, tracks, power equipment, control software, and maintenance packages to other countries. Maglev becomes not just infrastructure, but an export industry. Finally, Maglev aligns with China's long-term decarbonization goals. Electrified ground transport powered by renewable energy offers a pathway to reduce aviation emissions on heavily traveled domestic routes. For China, Maglev is not a gamble. It is a calculated investment in technological leadership.